Hey, Algebra 2, Lesson 40. It's the last lesson in our first unit of the curriculum, and it's almost Thanksgiving. I know, that's sort of funny. You'll be having your first end of unit assessment next week, so we'll spend a few days preparing for it. But today we're going to talk about obstacles resolved, a surprising result. The one thing that's really important that we're going to talk about today is called the fundamental theorem of algebra. Sounds really fancy, but it's actually very simple to understand, and we will get to it. I just want you to be prepared. Like, this is a main thing that we're going to make sure we hit on today. First of all, let's do 4 little quick review problems. Write each of the following quadratic expressions as a product of linear factors. Verify the factored form is equivalent. Okay, first one. I've got x plus and x plus. 27 works out into 3 times 9, and then 3 plus 9 is 12. So that does in fact work. I could FOIL that back and verify it, and that's how you would verify it. This next one is the difference of 2 squares, which is super simple. Let's move on. Okay, this next one, tad bit harder. So we're going to go ahead and I'm going to set that equal to 0 so I can move this to the other side. Take the square root of both sides, and that's where we get, I had to remind myself, I'm just kidding, I didn't, x plus 4i and x minus 4i. Let's just do this. We know we have negative 16, and the square root of it is plus and minus 4i, because I can't take the square root of a negative number. Cool. Okay, this last one, yeah, 5 doesn't factor into things that I can get a positive for. If I did x plus 1 and x plus 5, I would get a 6x in the middle, so that doesn't work. So I need to go straight to the quadratic formula, and you all roll your eyes, right? Negative b plus or minus the square root of 16 minus 4 times a times c all over 2a. Negative 4 plus or minus, let's see, 16 minus 20 is negative 4 over 2. So I get negative 4 plus or minus 2i over 2, which simplifies to negative 2 plus or minus I. So if I were to factor that, it'd be x plus, 2 plus I, and x minus, it's x plus again, sorry, 2 minus I. There we go, good review. Okay, we need to do just a tad bit of review. We talked about the remainder theorem back in lesson 19. Basically, it states that if you have a polynomial function, sorry, having pen issues, some polynomial that if you plug in a value and you get 0 for the polynomial, so you're plugging in some value a and it's 0, then x minus a is a factor of the polynomial. Okay, the remainder theorem plays a really important role in really the basis for this lesson. So we're going to link the solutions of a polynomial. That'd be the solution. We're linking the solutions of a polynomial back to the factors of the associated polynomial expressions. Okay? This right here is a quadratic expression. Okay, we've been working with these for quite a while. Every quadratic expression has two solutions that can be found using either the quadratic formula or just plain old factoring, if it's possible. But every quadratic formula has two solutions. These solutions lead to linear factors of the quadratic formula. So that's when we do, we'll give it to, let's see, A, B, C, D, and E. Okay, these are called linear factors. It's linear because this is just to the first power. Okay, this is quadratic because it's to the second power. So every quadratic equation has two solutions. Your solutions would be setting your linear factor equal to 0 and solving for it. In this case, it would be negative d and negative e. So every quadratic equation has two solutions that can be found using the quadratic formula or factoring. These solutions of the equation lead to linear factors of the quadratic polynomial. Okay? What types of solutions can a quadratic equation have? So again, I have ax squared plus bx plus c. That leads to two linear factors and two solutions. The quadratic equation has either two real solutions, one real solution, or two complex solutions. It's important also to remember that these situations right here correspond to either having two x-intercepts, can't spell, one x-intercept, or none, right? The complex solutions don't cross the x-axis. So that's a little reminder, okay? Let's move on to some problems. Okay, into example 1. So we're considering the polynomial p of x equals x cubed plus 3x squared plus x minus 5. The graph is shown right there. So looking at the graph, how do we know that there's only one real solution? We know because it only crosses the x-axis once. Is it possible for a cubic polynomial function to have no zeros? No. The shape of the graph doesn't allow that. Okay, basically the shape of the graph, this is a cubic shape, it has to cross the x-axis somewhere. I mean, even if it can cross it 3 times, it can cross it once, but it has to cross at least once. So from the graph, what appears to be the one solution to the equation? The only real solution is, let's see, x equals 1. So a factor of that would be x minus 1, right? We'll get to that next. And how can we verify this value is a solution? Well, we plug it in. So let's test it. P of 1. You have the polynomial there in front of you. I'm going to do 1 cubed plus 3 times 1 squared plus 1 minus 5. This gives me 1 plus 3 plus 1 minus 5 equals 0. Okay? If I get 0 as an answer, the remainder theorem tells us that that is actually a solution. So according to the remainder theorem, What is one factor of the cubic expression? There it is. Okay, let's move on. Factor out the expression you found in part E from the given. I found the easiest way to do this is to do some division. Okay, we haven't done that in a little while, so let's go ahead and practice it. If I know that, and I'm going to do synthetic division. So I'm going to list the coefficients, 1, 3, that'd be cubed, squared, first power, and constant. My solution was x minus 1, so I need a -1 here. Carry this down, I do some multiplication, and then subtraction, multiplication, and then subtraction. Wait a minute. 1 minus a -4 is +5. And then multiplication and subtraction. So this tells me my polynomial that's left over is x squared plus 4x plus 5. If you need some help doing the synthetic division, please ask. It's so much easier than long division, or if you remember the reverse, what was it called? The reverse tabular method. There's the word tabular. Synthetic division is pretty, I don't know, I think it's pretty fun. But I love math, so I guess I would think that. Although there's some math skills that I don't think are fun, but we still do them. So we factored out the linear factor that we already found of x minus 1, and there is our factored out part. So now we can figure out what the other two solutions are. So I need to factor this one. And I'm going to use the quadratic formula because I'm pretty sure I'm not going to get real answers. B squared minus 4ac. Oh, we already did this one. My answer was -2 plus or minus I, if I remember right. We did this one as one of our warm-ups. So, what are all the solutions? That looked like real, but it's not. What are all the solutions? I have x minus 1, x plus 2 plus I, and x plus 2 minus I. So my solutions are 1, 2 plus I, and 2 minus I. Cool. Negative. I'm so sorry. I knew there was something that didn't look quite right. There we go. H. Write an expression in terms of linear factors. I already did that in the last slide. I guess I was just working ahead. Sorry. So let's just write it again. X plus, oh, for goodness sakes. I get a little sloppy. X plus 2 plus I, and x plus 2 minus I. There we go. We're done. Just a really quick review. I had to look this up for myself because I didn't want to get it wrong. So I thought I would share it with you guys because I didn't want you to get it wrong. And I would have felt super silly if you would have asked me and I would have said, ooh, let me look that up. So I went ahead and looked it up. This is the sum of two perfect cubes. And then the difference of two perfect cubes. Okay, just a reminder, because we're going to use this in the next example. Alright, exercises 1 and 2. Write each polynomial in terms of linear factors. The graph of number 2 is provided. So this one, let's see, I can actually factor out an x first. I didn't need those sum and difference of perfect cubes, but you do need it for your problem set. Certain of that. So here we have, I can factor out an x first, and then I can factor the binomial. I would have x plus square root of I, oh, for goodness sakes. You guys are going to start counting how many times I say that in a class period, and x minus I square roots of 5. There we go. I'm not sure what this is. Let's get rid of it. Okay, and for this second one, the graph is there because I need my first point, and then I can factor from there. So one of my linear factors is going to be x minus 3, and I need to figure out the other one. So I'm going to go ahead and do some synthetic division, put all of my coefficients here. I need all of the coefficients represented, and I bring down the first term. So first I multiply, and then I subtract, because negative 3, yep. And then I multiply, and then I subtract, and then I multiply, and I subtract. And this has to be a 0 for your synthetic, that's my remainder. My remainder has to be 0. And then my first term is always squared. It's 1 less than what we start out with. My x term is 0, so I don't need to write it. So there, that's what we have. And then I can factor this to x plus 2i and x minus 2i. And then let's add that third one in there. Those are my 3 linear factors. Okay, I have a power of 3, so I need 3 solutions, whether they're real or not. Cool. Any questions, let me know tomorrow. But let's move on. Okay, let's discuss real quick. For the first exercise, I had x cubed plus 5x, and I had 3 solutions. For the next one, I had x cubed plus 3x squared plus 4x minus 12, and I had 3 solutions. What if I had x to the 4th plus lots of other stuff, or x to the 5th, okay, etc.? How many solutions would I have? Well, if I had x to the 4th, I would have 3 solutions. Whether they're real or not, I still need 3 solutions. Sorry, 4 solutions, 4 linear factors. Okay, 4 to the 5th power, I would still need 5 solutions, or 5 linear factors. That's the fundamental theorem of algebra. It states that whatever degree your polynomial is, that's how many solutions you're going to have every time. Okay, they may be real, they may be not real, but the fundamental theorem of algebra states that the degree polynomial we're working with will have a solution of that degree. We'll have that degree linear factors and that degree solutions. Not necessarily that degree of x-intercepts, but everything else will hold true. So let's try another one. Consider the polynomial function given, whose corresponding graph is given. How many zeros does p have? Okay, since we have 2 x-intercepts, there appears to be 2 zeros. Okay, the problem says that we are guaranteed 1 0, but because of the graph, we know that there are at least 2 zeros. Letter B, identify 1 0 from the graph. It looks like I have 1. Okay, 1 0 is in fact 1. Use polynomial division to factor out one linear term from the expression. So if I had a 0 of 1, that means I'm going to use synthetic division to factor it out. My coefficients are 1, negative 3, 6, negative 12, and 8. Carry that first coefficient down, multiply, I get negative 1, and subtract. Negative 3 minus negative 1 is negative 2. Multiply and subtract. multiply, and subtract, multiply, and subtract. I should always get 0 there. So now I have x minus 1 and x squared, nope, cubed, because I started out with the 4th power, so I need cubed. X cubed minus 2x squared plus 4x minus 8. So there we go. Now we have a cubic polynomial to factor. We know by part 1 of the fundamental theorem of algebra that a polynomial function will have at least one 0. What is that 0 in this case? So if you look back at the graph, it crossed the x-axis at 1 and 2. We already used 1, so we have 2 left over. So this polynomial function right here can have a 0 at 2. The original one, we already used the 0 at 1, so the one that's left, one of its zeros can be at 2. So I can actually use synthetic division and that cubic polynomial to figure out what my quadratic polynomial is going to be. So multiply and subtract, multiply, subtract, multiply, subtract. So I have x squared plus 4 left over. We just did this. I apologize. I got ahead of myself again. So we used polynomial division to factor out another linear. So we had x minus 1 and the cubic polynomial, and then x minus 2, and what we just got out of the division again. So that's where we stand right now. Okay, are we done? Can we factor this polynomial further? Yes, if we have a squared, we can factor it further. The squared factors to x plus 2i and x minus 2i. So all of our factors are x minus 1, x minus 2, x plus 2i, and x minus 2i. Now that the polynomial is in factor form, we can quickly see how many solutions there are to the original equation. Okay, we got 4. I'm not going to write them out again. Well, those were the linear factors. I can write out the solutions. I had 1, 2, 2i, and negative 2i are my solutions. We only had 2 x-intercepts, but we will have 4 solutions. So we have 4 solutions and 4 zeros. And I'm not sure if that needs an e. And then 2 x-intercepts. Cool. So what if we had started with a polynomial function degree of 8? Well, we would have 8 solutions, 8 zeros, and we don't know how many x-intercepts, right? We just don't know. So we have our lesson summary. Every polynomial function, degree of n, if n is greater than 1, has n roots over the complex numbers counted with multiplicities. Remember, we have multiplicities. If we had a solution of 1, I don't know, x minus 1 and x minus 1, that would be a solution of 1, multiplicity of 2. Therefore, such polynomials can always be factored into n linear factors, and the obstacles to factoring we saw before have all disappeared in the larger context of allowing solutions to be complex numbers. Okay, fundamental theorem of algebra we discussed. If we have a degree greater than 1 with a real or complex coefficient, there exists at least one number r, real or complex, such that it's actually a factor of the polynomial. Your remainder would be 0. The other part of the fundamental theorem of algebra is that if we have a degree greater than 1, then the polynomial has exactly that many zeros, that many solutions. And that's where we see right here. Awesome. So we're going to be factoring for our problem set.